Okay, so we continue the material in section 6.3, and we still talk about the third case. I mean irreducible quadratics. So last time we have talked about this example. For example, we know that 2x cubed plus 1 over x squared plus 1 dx. And we could rewrite this function by this way. Use the long division. It's of the form 1 subtract 2x over 1 plus x squared dx. So it's of the form some polynomial plus this one. And we say the reason we say irreducible quadratics, it means that here the denominator is 1 plus x squared. And you will let 1 plus x squared be 0, x squared equals -1. It doesn't have any real numbers. It has no real roots. And if you check its discriminant, a is 1, b squared is of the form a squared plus ax squared plus bx plus c. So b squared subtract a 4ac is equal to 0 subtract 4 times 1 times 1. So it's -4 is less than 0. So if its discriminant is less than 0, then we say that it's irreducible quadratic. For example, this one, irreducible quadratic. Okay, so now let's talk about more examples. To finish this case, we will talk about more examples. Here we consider this case. 2x cubed plus 4x squared plus 8x plus 3 over x to the power 3 plus 3x plus 3x. This one. Okay, yeah, so what's this? So let's see this one. It's integral. Okay, but before that, let's recall or let's see this result. Before that, let's see this result. Note. For this result, I think it's the result in section 6.2. Section 6.2, what's the integral of 1 over x squared plus a squared? X squared plus a squared. This one? Yeah, in section 6.2, we could solve it by trigonometry substitution rule. Trigonometry substitution. Okay? So, as we say, yeah, here we can see a right triangle, and we have 3 lengths of this right triangle. So it's xa. It has a form, so we will consider xa, x squared plus a squared is square root. So if you consider these 3 numbers, which one is the longest one? Of course, it will be this one. And we will put these 3 numbers in this right triangle. So it's the longest one, so it must be in the hypotenuse. Square root of x squared plus a squared. Right? Here. And x and a, we still have x and a. X could be here or x could be here. But as we say, in section 6.2, we use for the trigonometric substitution, we use these 2 right triangles. Here is theta. If we let hypotenuse be 1, opposite side is sine. Adjacent is cosine, right? So constant, it should be in the hypotenuse, or this case, let theta be this angle, and we let adjacent be 1. Then opposite is tangent. And hypotenuse is secant. hypotenuse is second. Okay, I will always use these two right triangle to explain this kind of question. Anyway, so you could see the constant one. It should be in the hypotenuse or in the adjacent side. It's adjacent. So, but here square root of x squared plus a squared is not a constant. So now constant is not in hypotenuse. So constant should be in the adjacent. So here is our constant a. So it's, in other words, x is over here. And it's our theta. So we should compare with this right triangle. It's our theta, it's our a, it's our a tangent. Compare with this one. We could not use this one, so now we use this one. So up this side is a tangent, and E is a secant. E is a secant. In other words, we let x. In other words, we let x equals a tangent. That is equals a tangent. Then you could see that square root of x squared plus a squared is equal to a secant. It's equal to a secant. Yeah, probably we remind you again. And how about its dx d theta? Here, this term is dx d theta equals a times secant square. Tangent is derivative is secant square. Secant square, right? So here we have dx equals a secant square d theta. A secant square d theta. So you have this result. This one. 1 over x squared plus a squared. X squared plus a squared is equal to square root of x squared plus a squared. It's square. It's square. Right? So now this term inside is a secant. So it's a secant is square. So it's a secant is square. A secant is square. But don't forget that a secant dx, dx you also need to rewrite it. You also need to rewrite it. dx equals a secant square d theta. A secant square d theta. This one. This one. Okay, so now take is square, so it's a square times secant square, right? And we could cancel secant square. And here we have a square, so we cancel one factor of a. One factor of a. So finally we have 1 over a, and we take out, so it's integral 1 over a d theta. So 1 over a is just a constant we could take out, and the integral 1 d theta. The variable is theta, so it's 1 over a theta plus a constant c. Plus a constant c. But here x equals a tangent, so you could rewrite it. I mean tangent theta equals x over a. Tangent theta equals x over a. So in other words, theta equals arctangent x over a. We should express theta in terms of x. In terms of x. So finally it's 1 over a times arctangent x over a plus a constant c. Just remind you this result. Again, this one. So for this one, you could use this formula directly. For this one, you could use this formula directly by triangle substitution. We could get this result. So okay, so for this integral, we know that it's of this form. So once we have this form, in this case, in this example, now we could come back to this example to solve it. We will come back to solve this example now. Okay. Okay, so now we come back to this example. Here, our question I write down over here. It will be better. 2x cubed plus 4x squared plus 8x plus 3. X cubed plus 3x dx. This one. Okay, so here, yeah, so first of all, numerator, denominator, both of them, their degree is 3. So we use long division. 2x cubed plus 4x squared plus 8x plus 3 divided by x cubed plus 0 times square plus 3x plus constant 0. So we need to multiply by 2. Then we can get 2x cubed plus 0 plus 6x plus 0. And the subtraction 0, 4x squared plus 2x plus 3. Yeah. Okay, so it's over the form. We could rewrite it. So the quotient is 2. The remainder is this guy. Okay, so it means that the numerator equals 2 times this one. Numerator equals 2 times this one plus the remainder. So for this 10, means it's 2 times x cubed plus 3x over x cubed plus 3x. Plus the remainder is 4x squared plus 2x plus 3 over x cubed plus 3x. This one. We separate, so we can get this one. And for this term, we cancel them. So it's over the form 2 plus x cubed plus 3x. Numerator is 4x squared plus 2x plus 3 dx. This one. Okay. Yeah. And this 10 is easy to see. This 10. Now we want to solve this 10. Okay. We want to solve this 10. Okay. So now we focus on this 10. So here we can see the 4x cubed squared plus 2x plus 3. X cubed plus 3x. And x cubed plus 3x, it has a common vector x. So we could take out the common number x. So it's equal to x times x squared plus 3. And this 10 is linear factor. This 10 is reducible quadratic. So it must be over the form. Separate x. Here is x squared plus 3. And linear factor, its degree is 1, so its degree is 0, so it's a constant a. Let me see, I write down this 10 for 3. Okay, and this 10 is irreducible quadratic. So actually, if you see, it's discriminant. It's equal to b squared subtract 4ac, so it's still a negative number. So actually, it doesn't have any real root. Negative 3. So it could not happen. So it's irreducible quadratic form. Okay, so the degree is s squared. The degree is 2, so we could label it by bs plus c. But now we should figure out the constant ABC, capital ABC. So we use the similar way. I mean, for this equation, it holds for any real numbers. So we multiply by, but it's not polynomial equation. So we multiply by this guy to get to solve it. So we multiply by, again, similar one, multiply by s times s squared plus 3. Then we can get left hand side, we have the numerator 10 equal to, here is a times, we cancel x, so we have a vector of x squared plus 3. Plus, we cancel x squared plus 3, so we still have x times this guy. bs plus c times x. Okay. And we do the distribution. Capital AX squared plus 3a plus bs squared plus cx. Okay. Actually, for this one, yeah, we could use the compare coefficient to solve it. if it has irreducible quadratic, then I think compare coefficient, then we could solve it. So for s squared, we could combine them. So it's a plus b s squared plus cx plus 3a plus 3a. Okay, so it's something like we let s be 0, it's 0, 0, 3 equals 0, 0, 3a. So for constant, we have three equations. If we let x be 0, you will get the constant 10. It will be the same. Constant 10, it will be the same. And now for the degree 1 coefficient, for x is degree 1, its coefficient is also the same. 2 equals c. 2 equals c. The last 10, I mean s squared, its coefficient is also the same. Compare coefficient, we have this result. 4 equals a plus b. Compare coefficient, we have this one. Since this equation holds for any x, so we could use compare coefficient way. Use this one to solve it. So here we could get capital A equals 1 and C equals 2, and plug in the number A, so you could get B equals 4 subtract A, so it's 3. It's 3. So we have this one. So we have this one. Okay. So now we could figure out the constant ABC. So now let's write down this 10. So it's equal to 2 plus, for this 10, capital A is 1 over x plus 3x plus c is 2, s squared plus 3 dx is equal to this one. It's integral. It's integral. Okay, so separate. First 10, 2 is integral. We have 3 10. We could separate. Consider each 10 to figure out their integral. Okay, first 10, 2. Second 10, 1 over x. Third 10, we also separate. 3x times s squared plus 3 plus 2 over s squared plus 3. Separate. And the first 10, 2 is integral is 2x. 1 over x is integral is natural log x. It's absolute value. Okay? And this 10, again, if it's of the form, in denominator is s squared plus some constant. And if you see, if it's a form, numerator is some constant times x, then you always could do it by this way, by substitution rule, right? By substitution rule. It's a product of two functions, and another one is inside function's derivative. It's inside function, this one is derivative 2x. So it's, I mean, if we multiply by 2 over 3, we can get it's exactly its derivative, right? So in this case, we could use substitution rule. Let u be inside function. So let u be inside function. You will get du dx equals 2x, right? And we could multiply by dx in both sides. Du equals 2x dx. Yeah, and this 10, so we could rewrite it. Now, 1 over s squared plus 3 is this one, 1 over u. But 3x dx, how about 3x dx? For 3x dx, we should multiply by 3/2 in both sides, right? We multiply by 3 over 2. We multiply 3 over 2 in both sides. So 3 over 2 du equals this one. Yeah, 2. So, okay, so it's equal to here we replace by u, so it's 1 over u times 3s ds is 3 halves du. This one. And it's equal to, it's constant, we could take out, times 1 over u is integral, so it's natural log u, it's absolute value, plus a constant c. And the final term, put it down, so it's put it back. So it's u is x squared plus 3, and it's always positive, so we could skip the absolute value. So it's x squared plus 3 plus a constant c, this one. I mean, it's integral. Okay, so this term, its integral is plus 3 over 2. Natural log x squared plus 3. This term. And this one, 2 over x squared plus 3. And for this result, I mean, you could use this result directly. 1 over x squared plus a squared dx. It's 1 over a. The integral is 1 over a times arctangent x over a. This one. Especially if a equals 1, then it's arctangent x. The integral is arctangent x. Okay, so now it's equal to 2. We take out the constant, 2 times this guy. But in this term, a equals, if you compare with these two terms, a should be, here 3 is square root of 3, it's square. So a should be square root of 3. So you write down this, plug in square root of 3. Then it's 1 over square root of 3 times arctangent x over square root of 3. This one. This 10. And finally, plus a constant c. Then we are done. Okay, then we are done. Okay, I think it's the okay, I think it's the result in section in case 3. Okay, so finally we still have one case. But for one case, as you see, even in this case, it is a little complicated. So if it's of the last case, it will actually it's more complicated. So we just write down its form. But if you are interested in the example or the detail, then you could check it in your textbook. We should write down its form. Let me write down its form. Case 4. It's something like the previous case. Case 1 we talk about it's a product of linear factor. In the case 2, for linear factor, it has repeat root. So we can see a repeat linear factor. And then case 3 is irreducible quadratic factor. And so the last case is repeat irreducible quadratic. So it's more complicated. And that's why I say I just write down the form. And you could check some example by yourself or follow the result in textbook. So it's something of the form. Okay, it's something like this one. If Q of S is, for example, if Q of S here discriminant b squared subtract 4ac is less than 0, and for the irreducible quadratic, it has repeat root. root. Then we could write down in this form. So now we have four constants. Okay. For example, I just write down the form. For example, x cubed plus x squared plus x plus 1 over x squared plus 1 is squared. We always could rewrite in this way. X squared plus 1. We know that it's irreducible quadratic. So we always could rewrite it by this way. Here, x squared plus 1, and its degree is 2, so it's ax plus b. And it has repeat irreducible quadratic, so it's cs plus d. We always could figure out the constant a, b, c, d, such that this equation holds. Okay, and once we can write down this form, we could solve this kind of equation, Yeah. But it's more complicated, so yeah, if you are interested, you could check it in your textbook. Yeah, so I think all the results we have taught in section 6.3, we have taught all the results. Yeah. Okay. But here I think I could tell you one variety. Even in your homework problem, you could see some variety. Use substitution. Just some variety. You should use the partial fraction, the way in section 6.3 to solve it. But before that, you should use some variety. It's some variety problem. So you should use some substitution to get a form. For example, originally the example is this one. Square root of x plus 4 over x ds. For example, is this one. Okay, so what's the integral? So let me check something. Yeah. For this one, it's polynomial, but it's not polynomial. It's square root of s plus 4, right? So we could not use the partial fraction directly. But once we do some substitution, we could use it here. And as we say, actually, if you use this one is square root, it's x. So if you consider it's square, you will get s plus 4. So it's something like s. We just need to plus 4, then we can get it's square. This guy is square. So if we let it be u, then if we replace square root of s plus 4 by u, I think it will be better, because once you replace square root of s plus 4 by u, you will see u squared equals s plus 4, right? So now if we could rewrite it. For the square root s plus 4, it becomes u. It's simple to solve it. But even for x, it becomes complicated. But x, we could write in this way. U squared subtract 4. So even its power becomes 2, but it's also polynomial form. So it's also polynomial form. So it becomes a rational function. And we could use rational function to solve it. But we still have this term. You should be careful. Here, dx. So now for this function, we have rewrite it by u. So ds, we should rewrite by du. So here, our dx du equals divide by, take differentiation by u. So you will get 2u. Otherwise, you could start by this way or this way. That's fine. anyway, so you will get dx equals to 2u du, 2u du. Okay, so dx equals 2u du, this one. Okay, so now you can get it, you can see that it's 2u squared over u squared subtract 4 du. It's 10. It's 10. So it becomes a fraction. I mean some polynomial over polynomial. Right? Some polynomial over polynomial. Then you could solve it. Right? Okay. So here okay, so I think you could check it by yourself, and if you have question, we could talk about this one. Yeah. Now you could solve it. Once you have this 10, you could solve it. Okay. Okay, so it's the material in section 6.3. It's a material in section 6.3. So once we finish section 6.3, we will talk about the material in section 6.6. Yeah, so now I would like to talk about the material in section 6.6. Yeah, so we still have several time to talk about this. Section 6.6, improper integrals. Improper integrals. And before that, I think, yeah, anyway, I mean, anyway, okay, so section, yeah, actually for the tool in integral, for the tool, as we say, the result in section 6.1, 6.2, 6.3, they are enough because we have already known several tools to solve integral problem. But in section 6.6, it's just improper integral. So I will tell you the definition about improper integral. And once you know its definition, then actually for this kind of question, probably just use some tool in previous section to solve it. But you should know the definition about improper integral. So yeah, so let's see. First of all, let's recall. We have definite integral. So when we say integral from f of s ds from a to b, what does it mean? It means that we have a function y equals f of x, and we integrate this function from a to b to consider its area. This part to consider its area. Capital A is exactly its integral, right? So in this setting, you could see that there are two cases. First of all, the interval AB should be bound. It's finite. AB, the interval is finite. The interval is finite. Second case, the function f, it should be bound. It should be bound. F is bounded. F is bounded. So, but sometimes we could ask the question, if the interval is infinite interval, then what could we say about its integral? We also could use the way, actually we also could use definite integral to consider it's the case when interval is infinite. And if f is unbounded, we also could use the way, improper integral to define its integral. So we have two cases. The first case, we consider the case interval is infinite. Yeah. Okay. So we use some simple example. For example, we integrate this function 1 over a square from 1 to infinity. And we explain it by the graph. 1 over a square. 1 over a square, when s equals 1 is 1 over 1. So when s equals 1 is 1 over 1 is 1. When x equals 2 is 1 over 2 square, 4. 1 over 4, so it's something like here, over here. So when s approach infinity, you will approach 1 over infinity. So you will approach 0. And when s approach 0, you will approach 1 over 0 square. So it's infinity. So it's something like this one. So it's our function. Y equals 1 over a square. Now we consider the integral in this part. We consider the area. Here. Integrate this function from 1 to infinity is something that we consider this area. It could be approach infinity. Yeah, we consider this area, the area of this region. So, how to get this one? It's something that we know the definite integral, and we want to define its integral. And it's the case when interval is infinite. So we could consider this case. Denoted by B. Consider this area. We label it by red. We use the red color to explain it. So this part, its area is this part, its area is, we integrate this function from 1 to B. We consider, okay, I write down over here. Here, we consider this guy. 1 over a square dx. Integrate this function from 1 to B. This part. Integrate this area. This function from 1 to B to get this area. So what's this? 1 over a square is integral is, we could write it in this way, negative to the power negative 2. So when we consider use the power rule, this guy, if we consider derivative, then we should put down the power, and for the power we should subtract 1. But when we consider integral, for the power we should plus 1. So plus 1 is x to the power negative 1. But when you consider its derivative, it's negative 1 times x to the power negative 2. But its coefficient is 1, so it is negative x to the power negative 1. And plug in 1 and the b. This one. So you will get, and it means that negative 1 over x, plug in 1 and the b. So it's negative 1 over b. Subtract negative 1 over 1. So it's negative 1. This one. Okay, so it's subtract 1, negative 1. So it's 1. 1 subtract 1 over b. So its integral is this one. If we let b, of course we let b be which is greater than 1. And as you see, it will be less than 1. It will be less than 1. So it's positive. And now we consider infinite. The interval is, it goes from 1 to infinity. So it's something that will let b approach infinity, right? So actually we could define it by this way. Actually we could define it by this way. I mean, all we want is let b approach infinity. Then we can get its limit. This term is limit. It will approach 1 subtract 1 over infinity, 0. So it will approach 1. So once we let b approach infinity, its limit approach 1. In other words, its limit approach 1. Then in this case, we could define its integral. We could define its integral. So indeed, in this case, we define its integral by this way. I mean, its integral is defined by this way. We define it by this way. We consider the integral from 1 to b, the same function from 1 to b, and after that, we define it. And after that, we can let b approach infinity. So its integral is 1. Its integral is 1. Yeah. Okay. Okay, here I write down its definition. I write down the definition. For the definition, its integral from a to b f of s ds equals this one. Limit e approaching infinity from 1 a to b f of s ds. If interval is infinite, then we define it by this way. Here is from negative infinity. In this case, we also could define it by this way. Limit a approaching negative infinity and negative infinity, then we define separate. We separate, I mean, we can separate by any real number a. Yeah, we define it. We have 3 situations. I think I write down, I mean, it's defined in this way. It converges if limit exists. It converges if limit exists. Otherwise, we call it diverge. Because it's defined in limit, so if we say its integral converge, it means its limit exists. If we say the integral diverge, its limit does not exist. And once its limit exists, I mean its integral, its limit exists, we call it its improper integral converge, and it's defined by its limit. I mean, it will converge to its limit, its integral equals the value it converges. The value it converges. For example, if it converges to a, then its integral is equal to a. It's equal to a. Okay, yeah, and we still have another example, and we will talk about them in our next class. Okay, that's all.